Okay, so hello everyone and welcome to another ICTS virtual string seminar. Today we are happy to have Matthew Reece from Harvard with us, and his talk is titled No Global Symmetries with Applications to Axions and Cosmic Strings. Over to you.
Okay, thank you. Thanks for inviting me to talk. I'm going to talk about three recent papers, two of them written with Ben Heidenreich, Jake McNamara, who's a student at Harvard, Miguel Montero, Tom Rodelius, and Irene Valenzuela, and another one with Gigi Fan, Katie Fraser, who's another student, and John Stout. And these are all sort of loosely related to some common ideas about the absence of global symmetries and theories of quantum gravity. So let me give you an outline of the talk. I'm first going to give you a very quick review of some ideas about global symmetries and generalized p-form global symmetries. And then I'm going to have three sections of the talk, one about Chern-Weil global symmetries, which is one of the papers with Heidenreich and collaborators, one about how an axion potential can be generated by magnetic monopole loops, which is the paper with Fan and collaborators, and finally about the idea of completeness and global symmetries. And what I'm going to try to do is explain some of these ideas, but also explain to you why I think they might have some relevance for the real world. So I'm coming from the direction of particle phenomenology. So I see a lot of you in the audience are from more the formal end of high energy theory. So I apologize if I might say some things that bore you because you're familiar with them. But for me, a lot of this content is relatively new, and I'm excited about it because I think it does have real things to say about the world around us. So first, this idea that there are no global symmetries in quantum gravity, this is an old idea. It goes back at least to the time when people started thinking about Hawking evaporation and thinking about thought experiments, like what if I throw a lot of baryons into a black hole, can baryon number just kind of disappear? And in the 80s, Banks and Dixon proved that in perturbative string theory, if you have a global symmetry, you can actually construct a vertex operator that makes a gauge boson, and so it was really a gauge symmetry all along. And then in the last decade or so, there's been kind of a large number of new arguments along these lines. Banks and Seiberg wrote up an idea, which I think is older, but they have a very nice discussion of it, which is that if you had, say, an exact U1 global symmetry in a theory of quantum gravity, you could start making big black holes with very large symmetry charge, and you could just let them evaporate, and their Hawking evaporation doesn't see the charge because it's global and not gauge. There's no electric field you can measure outside the black hole that's going to affect the way it emits particles. And so sometimes it might emit particles with opposite charge and sometimes with the same charge, and its charge is going to kind of random walk. But if you wait long enough, a really big black hole can shrink down to a small black hole with kind of arbitrarily big charge. And in that way, there would be infinitely many different states in a finite mass range. And that sounds like a disaster for any sort of definition of a thermal ensemble, or just lots of ideas about thermodynamics and holography would break down. And there's another recent holographic argument from Daniel Harlow and Hiroshi Oguri, which is based on the idea of entanglement wedge reconstruction, which sort of says that if we have global symmetry operators, we can kind of factor them into operators operating on subregions of the boundary, and each of those operators only sees a small part of the bulk, and so you can argue that these operators would have to commute with any local operator that's deep inside the bulk. And therefore, there really is no such thing as a symmetry operator that acts locally in the bulk theory. Okay, so that's a very quick summary. They have a very long paper with lots of details. And in the last couple of years, there have been even more papers with variations on arguments about why we don't believe that quantum gravity theories have global symmetries. I should say that these arguments apply not only to U1 symmetries, which are kind of the setting of classic black hole arguments like this one, when you think about something like baryon number, but they also apply to discrete symmetries and to more exotic higher p-form symmetries. So we really think this is sort of a universal feature that quantum field theory is happy to have symmetries, but quantum gravity is really not. I should also say, feel free to interrupt me with questions at any time. Okay. So that was one idea that we believe to be true about quantum gravity. Another idea that we believe to be true about quantum gravity is completeness of the spectrum. And again, this is probably an old idea, all the way back when Dirac first figured out that electromagnetic theories allow objects like magnetic monopoles. I think it was sort of believed that these things should exist in nature because, if the laws of the theory allow them to exist, it would be surprising if somehow nature didn't take advantage of such things. But Polchinski articulated this in a very crisp way. He said that if we have an interacting U1 gauge theory, and I mean U1 and not R, so charge is really quantized, any such theory should have magnetic monopoles. And it's easy to find examples. We can have a UV complete U1 gauge theory that comes from starting with SU2 and then breaking it to U1 with an adjoint Higgs. And we know that this theory has the Atuf-Polyakov monopole. We have Kaluza-Klein theory, where we start with a gravitational theory and we compactify on a circle and we get a U1 global symmetry, and it has a Kaluza-Klein monopole, which is just some solution to the higher dimensional gravitational equations of motion. And the more general idea that kind of follows from this is that we expect that in a quantum gravity theory, we have some set of gauge symmetries. And we think that the lattice of all possible allowed charges should be filled. There should be some sort of object or collection of objects that has any kind of charge that's allowed in the theory. And Polchinski himself, of course, famously discovered some of these objects. It was known for a long time that the type 2 string has gauge fields in the spectrum, the Ramon-Ramon gauge fields, that had no obvious charged objects corresponding to them. And of course, the answer turned out to be that there were no perturbative charged states, but non-perturbatively, there are charged objects, and those objects are d-branes. And they appear with both electric and magnetic charges under any given Ramon-Ramon gauge field. And more recently, it's been understood that for U1 gauge theory, completeness is actually a consequence of the principle of no global symmetries. And this is something I'm going to come back to later in the talk. So these two ideas, that theories of quantum gravity should have all possible kinds of charged objects on the one hand, and that they should have no global symmetries on the other hand, actually turn out to be very closely related to each other. But to make that connection precise, at least in quantum field theory, we need to talk about something a little bit more general than the symmetries that we're used to. So that's something I will come back and say a bit more about. Let me introduce a convention I'm going to use throughout the talk when I talk about symmetries. A thing that we usually do in introductory quantum field theory is we talk about symmetries that have a conserved current, J mu, some Noether current, and it's conserved in the sense that the divergence of the current is 0. But there's kind of a dual language we can use, which is to rewrite things in terms of differential forms, which are given by the Hodge star of the current we started with. So basically contracting with an antisymmetric tensor. And if the divergence of your current J mu is 0, that means that D, the exterior derivative of the differential form that you get from star of J, is equal to 0. Okay. So throughout the talk, when I talk about conserved currents, I'm going to talk about closed differential forms. Okay, and if you're used to the other formulation where conserved current is something like J mu, just remember that they're related by taking the Hodge dual. And so in this language, when I talk about gauging a conserved current, instead of writing A mu, J mu, I will write one form gauge field A, wedge the D-1 form current J. And Maxwell's equations that tell us that the divergence of the electromagnetic field strength is the current becomes the statement that the exterior derivative of star of F, the two-form field strength, is equal to J. And so in particular, a current that has been gauged is now an exact differential form. Okay, so that's a stronger statement than just that it's closed or conserved. It's the derivative of something else. And this language is useful for talking about a more general kind of symmetry than the one that we're used to. So instead of just talking about closed forms which are D-1 forms, we can talk about closed forms which have any degree. And so we could talk about, for instance, in free Maxwell theory, we have two closed forms, which you can think of as conservation laws. One of them is just the equation I just wrote, that's Maxwell's equations, but with the current J on the right-hand side set to 0, because we're imagining we have no sources, no electric or magnetically charged particles. So D of star F is 0. That's a closed D-2 form current. In 4 dimensions, it's a 2 form. And we get a global D-3 form symmetry. In 4 dimensions, that's a 1 form symmetry. And we also have the Bianchi identity, that dF itself is 0 if there are no magnetic monopoles in the theory. And that's always a global 1 form symmetry in any number of dimensions. Okay, so in general, we're going to use this language of P-form symmetries. And we're going to have currents of general degree, and those will correspond to symmetries with one lower degree. Okay, so a Q form current corresponds to a Q minus one form symmetry. And because fluxes are quantized, if I take these things F or star F and I integrate them over some surface to try to get some charge associated with the symmetry, I will get an integer, and that means these symmetries are U1 symmetries. And the objects that carry these charges under the symmetries, in the case of star F being our current, are Wilson loops. Okay, so if I take a Wilson loop and I put a sphere surrounding it and integrate, I will get some electric flux associated with the Wilson loop. And if I do the same thing for an 't Hooft loop, which creates a magnetically charged probe particle, I integrate F and I get magnetic flux. Okay, so these symmetries you can think of as basically just counting the total charges of Wilson or 't Hooft loops. And in general, a one-form symmetry is something where the charged objects are one-dimensional, like line operators, like a Wilson line. Okay, and this notion has been formalized in a paper several years ago by Gaiotto, Kapustin, Seiberg, and Willett. They talk about these general p-form symmetries. A p-form symmetry acts on p-dimensional operators, and it's associated with a d minus p minus 1 form current. Let's see, I actually realized I scrambled the things on the previous slide. The d minus 2 form current is the one that's the one form symmetry in any number of dimensions, and the 2 form current is a d minus 3 form symmetry. Sorry, I corrected that on the slide and I've got it backwards on the previous slide. So the magnetically charged objects have different dimension. In 4D, they're point-like monopoles. In 5D, they're strings. In 6D, they're membranes, and so on. The electrically charged particles are always the same, so this one is always the one form symmetry. Okay, I apologize for scrambling that on the previous slide. So in general, what we have is a d minus p minus 1 form current that corresponds to a p form symmetry. And you can think of this relationship between the degree of the current and the dimension of the operator in terms of some symmetry operator, which comes from integrating the current over a surface. So we have some manifold of d minus p minus 1 dimensions, and we have an operator living on it, which we call u. And this operator can link with a p-dimensional object in the way shown here. This is the 3D case where these are both one-dimensional. A circle can surround a line. And there's a word identity associated with this, which is that when you act with this operator on the charged, you act with the symmetry operator U on the charged operator V. This acts according to some representation of the group element. And so you have one of these operators for every group element. The operators are invertible in that if you have an operator for G, you have another operator for G inverse, and they cancel each other. These operators are also topological in the sense that you can stretch them and distort them. And as long as you don't actually kind of cross through something charged and change the linking number, you won't change the correlation functions. Okay, so that's a very quick summary of these kind of abstract notions of these operators. And I'm going to be using some of these notions in the rest of the talk. So let me pause here and ask if people have questions before I move on. Okay, I don't hear any questions. So, so let me move on to part 2, where I want to talk about Chern-Weil global symmetries. And these are kind of generalizations of the symmetries, the conserved currents F and star F that we saw in U1 gauge theory.
Hello, sorry.
Yeah.
Can I ask a question?
Okay.
So is it always the case that whenever you have a closed form, you should have these p-form symmetries associated? Or is there something that in the theory can have these forms which are closed, but somehow there is no symmetry associated with them? Or is it like, is it a if and only if statement that whenever you have a closed form?
I think so. I guess what I would say is that probably the most interesting symmetries are the ones that are associated with compact groups. So one thing that might be a little bit of a borderline case is if I'm in D dimensions and I have a D form, it's always closed because there are no D plus 1 forms. And so it would maybe be a little not so useful to talk about every D form that you can write down in the theory as being a separate symmetry. But at least for things of degree less than D, I think this is true. And maybe what I should say is that here I've been talking about having conserved currents and getting operators from them, which applies to continuous symmetries like U1 or SU2. But this language of the symmetry operators applies even in the discrete case. Okay, so even if I had something like a Z3 symmetry, there's no local current associated with it. There's no Noether's theorem for this, at least not a straightforward version of Noether's theorem. But you can still imagine an operator that sort of acts locally and carries out a Z3 transformation on things that are charged. So I would say that the notion of symmetry is more general than the notion of current. Current applies only in the special cases of continuous symmetries. But I do think it's true that whenever you have a conserved current, you can construct these operators just by integrating the current over the corresponding manifold and getting an operator.
Sorry, so just another related question. So whenever you have a closed form like this, is it always true that there's some kind of some selection rules or something that some states cannot go to other states, the overlaps are zero, or are there always selection rules associated with every closed form? You know, like, do we know anything about that?
I think that's true. I mean, we always have word identities when you construct these kind of operators. Again, the case that might be a little bit degenerate is when the symmetry, when there's no quantization of the flux, for instance, your symmetry would be like R and not U1. And then the notion of charge becomes kind of continuous and things become a little bit weird. But yeah, I think that in general these things all come together. So word identities imply conservation laws, and they're associated with these sort of local conservation laws of currents.
Okay, thank you.
Mm-hmm. Okay. Okay. So now what I want to do is generalize this idea by noticing that in the U1 context we had df as 0. And so sort of a trivial consequence of that is that if I'm in high enough numbers of dimensions, I can construct things where I wedge multiple f's together. And d of those things is also 0. Okay, so if df is 0, d of f wedge f is 0, d of f wedge f in 6 or more dimensions is 0, and so on. And so in general, f wedge f is if there are no magnetic monopoles, we'll come back to what if there are, but if there are no magnetic monopoles, f wedge f is a conserved 4-form current and generates a d-5 form symmetry. In 4 dimensions, that sounds a little bit weird because it's a -1 form symmetry, and that's that sort of degenerate case where this is kind of automatically closed in 4 dimensions. But there's still something interesting about it, which is that its integrals over 4 manifolds are quantized. So it's not just any random -1 form symmetry, it's a U1. Okay, but maybe more interesting than the U1 case is the non-abelian case. So I can take a non-abelian gauge field and ask what is d of trace of f wedge f, which is a gauge invariant current, and again it's 0. And the reason is that I can move the d inside the trace, and then inside the trace you can check that replacing these d's with covariant derivatives dA of f leaves this equal to 0, but dA of f is 0. You can check that replacing these with covariant derivatives leaves it equal to the expression we had before, but then it's also 0 because the covariant derivative of f is 0. That's the non-abelian Bianchi identity. And this is an old fact about mathematics. This is a fact about mathematics that predates Yang-Mills theory, and it's something that if you've studied characteristic classes, you've probably seen this come up in some discussion, and so we call this Chern-Weil symmetry because this piece of mathematics goes back to the work of Chern and Weil in the 1940s. And so in general, we have this whole family of conservation laws that if I take some number of copies of the field strength and wedge them together, and I take the trace and then I take the exterior derivative, I get 0. And they all follow from the non-abelian Bianchi identity. And so every 2K form conserved current corresponds to a generalized d-2K-1 form global symmetry. And we call this whole family of things Chern-Weil global symmetries. And so the reason that this is interesting is that these symmetries are everywhere in gauge theory, but they're not easy to break because they follow from the Bianchi identity. But on the other hand, we believe that theories of quantum gravity can't have any global symmetries. And so we also believe that theories of quantum gravity frequently have gauge fields in them. And so I've told you that when you have gauge fields, you have these conserved currents, and they correspond to some symmetries. And that should puzzle us, because how can quantum gravity have gauge theories which automatically come with these symmetries if quantum gravity can't have symmetries? And well, in the case of the U1, we said that the symmetries were generated. The sort of simplest example of the Chern-Weil symmetries were the ones I mentioned earlier, where the current just is F or star F. And those symmetries can be broken if things appear on the right-hand side of the conservation law, which means magnetically or electrically charged particles exist. So in that case, we know how to reconcile the symmetry with quantum gravity. We just need electrically and magnetically charged objects to exist. But here we can ask, what's the more general story? And you should have some intuition about these symmetries from the fact that trace F wedge F is the thing that measures instanton number, right? So in 4 dimensions, you integrate trace F wedge F over your whole 4 manifold, and you know you have to get something quantized, and it's quantized in some basic units where a BPST classical instanton solution has instanton number 1. And in 5 dimensions, these instantons lift to world lines. You have something that's like the 4D solution times a time direction. And so these instantons become honest particles charged under a zero form global symmetry. And this is just kind of an ordinary global symmetry. And in 6 dimensions, your instantons become strings and so on. So we have charged objects, but the existence of those charged objects does not break the conservation law. So the question is, what happens in quantum gravity? How does it eliminate these symmetries? And maybe before I talk about any detail, I should just say that in general, you should imagine there are 2 things you can do. One is to gauge the symmetry. Okay, so then we get the stronger statement that these things are not just closed, they're exact. The other is to break the symmetry, but breaking the symmetry somehow has to happen in the UV, because it follows from the Bianchi identity, which the gauge fields in the EFT obey. So you have to somehow go beyond the effective field theory and imagine that your gauge fields emerged from something else that was under underlying description. So we'll take a look at some examples of both gauging and breaking of Chern-Weil symmetries. And the first thing I want to do is talk about, oh, sorry, question?
Yeah, I mean, why can't you just, there is an operator in this theory, which is kind of like an analog of a monopole operator. And so you can just say that there exist such operators in the UV, which break the symmetry in the UV Lagrangian.
That's right. So you're saying maybe in the UV there's an operator that kind of
but we can define
sort of
it
creates
in the IR by the same way we define a monopole operator in abelian gauge theories. You eliminate a point from the manifold, and then you impose the condition that the topological charge around that point, which is a force topologically, is unity in some normalization, and that's an operator. That's a valid operator in this.
That's right. So if we're in 5 or more dimensions, we can certainly do that. And 4 dimensions, again, is a little bit of a weird degenerate case. But yeah, you can cut out a region of your manifold and define some boundary conditions. And that what do I want to say?
But we do that all the time. 't Hooft loops are defined like that. Monopoles are defined.
Right. But so 't Hooft loops do not imply that magnetic monopoles actually exist, right? So the fact that 't Hooft loop operators exist does not mean that the conservation law df equals 0 is invalid, because 't Hooft loops basically create kind of infinitely heavy probe monopole world lines that are sort of static objects in the theory that you put in to probe the theory. They don't create dynamical monopoles. So this is kind of analogous. You could imagine that there exists something like this, some sort of dynamical thing. So like in 5D, where instantons are just like particles, you could imagine that there are some sort of like dynamical instanton particles and operators that create them, rather than just sort of rigid static field configurations that we can talk about. And that's right. That is one way to break the symmetry. So I agree. But In the quantum gravity context, it turns out that sometimes these symmetries are gauged, which is kind of a different thing than breaking them. And so we actually see both. But yeah, there are cases where something like what you're saying, I think, is a good way to understand the fate of the symmetry.
You could also formulate, well, I don't know whether that's satisfactory, but you could formulate such a theory as a sum over these world lines with some weight in that language. It's maybe not a usual representation of matter fields, but you could sum over all world lines which carry this this charge. And but in any case, I mean, I don't think conceptually it is an obstacle, even if we can't define it maybe in a usual way.
So maybe what I should say is in the example of the current being F, when we have the conservation law dF equals 0, there are basically two ways to break that conservation law, both of which happen in examples in quantum gravity. And one is that the conservation law is just broken by the existence of monopoles. Okay, so dF equals some magnetic current, and that's like what you're talking about. You know, then there's some operator that can actually create a physical dynamical monopole, and the current is broken. The other thing that can happen is you can gauge the symmetry F. And so you do that by having a BF theory. You have some external gauge field B, and you have a B wedge F term in your Lagrangian. And that also happens in examples within quantum gravity. And in that case, we give a mass to the gauge field, and it becomes heavy. But in some sense, well, in some sense, it's still sort of there. We can still talk about the field and its fluxes and things. It's just that it's become massive, and we've broken the conservation law. So both of these things happen for the case where the current is F, and generalizations of these things happen when it's trace F wedge F, for instance.
Thanks.
Okay. So I want to talk about an example of what can happen, and this also ties into the second story that I want to tell you. So let's think about a case where our gauge field is SU2, our gauge theory is SU2, and it's broken to U1 by an adjoint. Okay, so this is a theory where we know that magnetic monopoles exist, the Topf-Polyakov monopoles exist. And so we know that the current, in the infrared theory, the current F wedge F is broken because dF is not 0. dF is the magnetic monopole current. But there's an interesting sort of puzzle you can ask here, which is that in the UV, we had an SU2 theory, and it has this current trace F wedge F, and that's conserved. And so we seem to have a conserved current in the UV that got broken in the IR. And one question we could ask is, well, if this was really a conserved current in the UV, why can't I gauge it? And if I gauge this current, then how is that consistent with it being broken in the IR? We can't gauge things that are not conserved. So there's a little bit of a puzzle. And the answer to this puzzle goes back to some nice physics that was worked out in the mid-70s by Zhakiv and others, which is that the classical Topf-Polyakov monopole solution has collective coordinates or zero modes. And the obvious zero modes are translations. You just move the monopole around. But there's a less obvious zero mode that the Topf-Polyakov monopole has, and it is it's coming from kind of a large gauge transformation, a U1 that does not go to the identity at infinity. And this leads to a collective coordinate which behaves like a compact scalar boson, which I'll call sigma, that lives on the monopole world volume. And in 4 dimensions, the monopole world volume is a line. So the theory on the world volume is just quantum mechanics. And this theory is just the quantum mechanics of a compact boson, which is just a particle on a circle. And you can excite this particle. It has momentum eigenstates going around the circle. And these momentum eigenstates correspond to giving the monopole electric charges. Okay, so you can check that this world volume degree of freedom that just spins in a circle, because it came from these kind of U1 gauge transformations in the bulk 4D theory, it corresponds to giving the monopole electric charge. And the same thing holds in more than 4 dimensions. It's just that now our theory on the world volume is a QFT, not just a quantum mechanics theory. So I can't talk about energy eigenstates in such a simple way, but the principle is basically the same. it turns out that because of this world volume degree of freedom, we actually can construct a conserved current. And so what happens is in the bulk, we started with SU2 and we gauged trace F wedge F. And how do we gauge it? We have a Chern-Simons term that couples some external gauge field C to trace F wedge F. Okay, so this is like the analog of a BF term in the case where the current was just F. And after we Higgs, trace F wedge F obviously matches onto F wedge F in the bulk, but it also matches onto something localized on the monopole world volume. So you can think of this monopole current as like a delta function that sticks you on the world volume. And there's a current which is the monopole current wedge d sigma, or actually the covariant derivative of sigma on the world line. And this UV coupling turns into this IR coupling, and this whole thing in the IR turns out to be conserved. Okay, so DF gave us a magnetic monopole current, but on the monopole world line, basically, there's a Stuckelberg mechanism that d sigma is essentially equivalent to A, and so when D hits that, it matches F, and these two terms cancel each other. Okay, so gauging this thing in the bulk required this localized degree of freedom on the monopole that lets it turn into a dion, and leads to a new kind of Chern-Weil current in the IR theory, which is a linear combination of these two different things, which individually are not conserved, but taken together are conserved. And this is nothing other than the Whitman effect. In 4 dimensions, to gauge a 4-form current, I have to couple it to a compact scalar, theta, which is like an axion. And the coupling on the monopole world line is kind of the 1D version of a theta term. It's theta times d of a compact scalar. And this implements the Whitman effect. When you add this term to the monopole world line and you recompute your momentum spectrum, it's now shifted. And the electric charge picks up a piece that's proportional to the magnetic charge times theta. And so this is what Whitman derived in the late 70s. And one way to think about this is that the Whitman effect is something that is sort of necessary to consistently be able to talk about these Chern-Weil symmetries and to gauge them consistently. Okay, so if you didn't know about the Whitman effect and you were thinking about these symmetries, you could have been led to stumble on the Whitman effect by trying to figure out how to make this story consistent. Okay, so that's one story of how Chern-Weil symmetries can be gauged. And the moral of the story is that they can be gauged, but the gauging sometimes brings in this extra structure. Okay, so here we have these world volume degrees of freedom. And I won't have time to talk about it today, but you can check lots of examples in string theory where you ask, how is some Chern-Weil current gauged? And often the consistency of that requires the presence of degrees of freedom localized on branes. And so a lot of the structure of the D-brane Lagrangians in string theory, it's been derived from many different viewpoints. But I guess I would say, given sort of the textbook version of things as I learned them, I had the impression that a lot of these were sort of special facts that come from starting with a highly supersymmetric theory and sort of deriving what the structure is. But here we sort of get the impression that, in fact, a lot of them are really necessary for consistency reasons. So string theory has to get rid of all these unwanted Chern-Weil symmetries. And it gets rid of a lot of them by gauging, by having Chern-Simons terms. But then the consistency of the Chern-Simons terms requires degrees of freedom that are localized on world volumes. Okay, so lots of old stories about the Whitman effect and anomaly inflow and things like that can be thought of as being part of this consistent gauging of Chern-Weil symmetries.
Sorry, one quick question. Does this conjecture, it sounds like it's implying immediately an existence of an axion, just because you can't have, well, in 4 dimensions, it's kind of weird. This is a -1 form symmetry, right? So right. I'm not sure whether, does the gravity exclude possible global -1 form symmetries or not? Is that also a constraint?
Yeah, that's a great question. And I don't know that I have a definite answer, but I would like to believe that that's true.
I mean, if it's true, it solves the strong CP problem, right?
Well, it at least would tell us that an axion exists, and that goes a long way towards solving the strong CP problem. Solving the strong CP problem requires something stronger than that, because you need that there are no other contributions to the axion potential that kind of shift the minimum away from the one determined by QCD. That's something I could say more about. Maybe I can come back to that at the end if there's time. Actually, there probably won't be time because I'm running a little behind schedule. But yeah, it seems to be true when we look at examples in string theory that we don't find these -1 form symmetries. They're always gauged or broken. And yeah, I would like to argue that tells us that axions should exist in the real world. But because -1 form symmetries are kind of on a different footing than higher p form symmetries, I don't know how to make that argument in a really convincing way. It is true that a lot of times in the string theory context, our gauge fields originated in higher dimensions. And so within the higher dimensional theory, trace F wedge F is a different kind of p form symmetry. And you can sort of make the argument there that it's gauged by some Chern-Simons term. And when you compactify to 4D, you get an axion by starting with the gauge field in higher dimensions and
Right.
integrating it over some cycle or something. But if you had sort of intrinsically 4D gauge fields like living on D3 branes or something, then I don't know how to make that kind of argument. So yeah, I think that's a great question. I would love to hear if anybody has insights on it. I think if we had a really good argument that quantum gravity can't have -1 form U1 symmetries, then we would have a fairly persuasive argument that that there should be an axion in the real world, and that would be exciting.
So, sorry, I have a question about this. Maybe I should have asked this earlier. The question is that these arguments about quantum gravity not allowing global symmetries, they don't really tell you, whether you can have a very good approximate symmetry, right? I mean, you could have a symmetry that's broken by something extremely small or some extremely operator very high up in the UV. So, I mean, when we want to make a statement like, you have to have axions in the real world, how do you get around this obstacle, which is that this doesn't tell you, at what scale the symmetry should be broken, where.
Yeah, I agree. A lot of what I've been thinking about the last few years are these kind of questions of how do we take these no global symmetry arguments and try to sharpen them into something that's actually useful for phenomenology. And things like the weak gravity conjecture go in that direction. So yeah, I think you're right. That's sort of tied into this other question about what are the other contributions to the axion potential. So QCD would generate an axion potential that would do what we want. But if there could be some other source of a really big mass for the axion that's unrelated to QCD and could have a misaligned phase, then you don't end up in the right CP preserving minimum. Yeah, I don't necessarily have a good answer to that. I think what this Chern-Weil perspective suggests is that if you have other things that generate axion potentials, let's see, I might have a backup slide on this somewhere. Let me see if I do, since the question is coming up. I was not planning to say this today, but so one thing you worry about with axions is if you have some hidden sector gauge group that confines and talks to the axion, it could generate some new contribution to the axion potential, which adds to the QCD contribution. And if there's some relative phase, that could completely spoil the solution to the strong CP problem. From the perspective of the Chern-Weil symmetries, if these are two different gauge groups, they each have their own trace F wedge F, and the axion would be gauging one linear combination of those two global symmetries. But quantum gravity is not allowed to have any global symmetries. And so if we gauged one linear combination, you should ask what happened to the other one. And one possible answer is that it was also gauged, in which case there would be a second axion around. And when this first gauge group confines at some higher scale, it would give a mass to one linear combination of the axions. We can integrate that one out. And we're left over with another linear combination talking to QCD, and that has a good chance of still solving the strong CP problem. There might be some residual kind of shift from mixing with the heavy thing, but if there's enough of a scale separation, then that can be small. Another possibility is that these two different Chern-Weil symmetries are not really independent at all. And so there was really only one symmetry in the UV, and that's actually what my next slide was previously going to be, but let me just say it now. If you have different gauge groups that unify into one gauge group in the UV, you really only had one trace F wedge F to begin with. And that would allow this kind of structure where one axion talks to both, but it would also mean that you might expect some relationship between the actions and the phases that appear here because they're coming from the same underlying thing. So it doesn't necessarily solve the strong CP problem. It doesn't necessarily, this is what we call the axion quality problem, which is kind of the higher order version of the strong CP problem. You know the axion would do the job, but then you start to worry what protects the axion. And what this suggests is that at least some of the things you might have worried about in quantum field theory might be mitigated in quantum gravity, but not necessarily completely solved. And again, there are lots of other things that can contribute to axion potentials. There are these axion monodromy kinds of models, which are different kinds of couplings. So there are lots of things to think about, and I'm not going to claim that the problem is trivialized when you say the axion exists. But at least it gives you a new perspective on the problem, and maybe makes some of the concerns more mild than they would be just in pure effective field theory.
Okay, thank you.
Okay, thanks. These are good questions. So now, right, in fact, I think we've basically covered the territory on my next two slides. I was going to say this about different gauge groups can unify. We've just talked about that. And then I was going to talk about axions, and we've been talking about that. So so thanks. So with that, let me move on to the next topic, which is also axion related, which is that axions can get potentials from groups of magnetic monopoles, and this is quite closely related to the things I've been discussing. We're used to the fact that an axion that couples to trace F wedge F for a non-abelian gauge group can get a potential from Yang-Mills instantons, as in the case of QCD. It's complicated by the fact that there's an infrared divergence because these instantons have a size modulus, and so confinement sort of makes this whole story more complicated. And but at 0th order, we can just say the axion gets a mass from instantons. And in the abelian case, if I have a theta F wedge F coupling, there are no U1 instantons on R4. And so you might say there's nothing analogous. And this is what people have usually said. So there's lots of phenomenology thinking about dark matter, which doesn't necessarily solve the strong CP problem, but might be an axion that couples just to the photon or to dark photons. And people usually say the mass of that axion is kind of unrelated to this coupling. But we know that in the presence of magnetic monopoles, this theta F wedge F coupling has a physical effect, and it's the Whitman effect that we were discussing. And I've already mentioned the Whitman effect, but let me just say a few more words about it. In the presence of the axion coupling, our equations of motion and electrodynamics change. So we have our usual magnetic Gauss's law, but our electric Gauss's law changes, and it changes in a way that depends on theta times the divergence of the B field. And so this just comes from taking the equation of motion in the presence of this theta, this abelian theta F wedge F term. And so what you derive from that is that in the presence of a magnetic charge and a theta angle, you induce an electric charge, and this electric charge is proportional to theta. And when we shift theta by 2 pi, we have to get back to the theory we started with, but the monopole through the Whitman effect acquires an electric charge and becomes a dion. And so if the theory we started with had just a monopole, we go around by 2 pi, we get a dion, but the theory should be the same. So somehow the dion should have already existed. And we can keep going that way and build up this whole tower of dionic excitations. We'll have a monopole ground state, and then we'll have dions of charge 1 and charge 2 and charge 3 and so on. And I was telling you about the story with the Atuf-Polyakov monopole, where there's this degree of freedom, this collective coordinate that whose excitations correspond to these dions. But what you see from this logic of the Whitman effect is that's not special to the Atuf-Polyakov monopole. That had to be there for any monopole that has a theta F wedge F term. That's the only way the story can be consistent. And so there's some set of excited states, and their mass depends on the electric charge, and there's some sort of splitting between them. And so we have the set of dions. They have integer electric charge shifted by theta over 2 pi. And there's some energy spectrum that depends on the square of n minus theta over 2 pi. And so individual monopoles have a mass that's not periodic in theta, but the whole tower is periodic because there's this kind of monodromy that each state kind of shifts over to become the next state when you go around the circle. And so this is all well-known old physics, but what I want to say that as far as I'm aware, nobody had pointed out before is that this implies that when you integrate out all of these dions, you get a potential for the axion theta. And there are two different ways to think about this calculation. One is we can integrate out kind of each dion one by one and get some sort of Coleman-Weinberg-like potential, and we can add them all up. The other is we can think of this as kind of a semi-classical calculation where we sum over monopole world lines that are inserted in the path integral. And these monopole world lines have this extra collective coordinate associated with sigma, this dion degree of freedom. And that's a compact scalar. And so you can imagine wrapping the world line around that direction. Okay, so from the point of view of the monopole, it's almost like there's an extra dimension they can propagate in, and their world lines can wrap around it. And we can sum over things with different winding number around the circle. And it turns out that these two different viewpoints are the same calculation rewritten with Poisson resummation. Okay, so we can start with kind of the standard expression for the loop of a massive particle written in this kind of world line language where we integrate over Schwinger proper time, and then we sum over all the different dions, and we get some expression like this. And if we Poisson resum, this sum over n turns into a sum over some other integer L, which behaves like winding. And when you do the integral, you get a formula like this. So there's some effective potential for theta. It's a sum of harmonics that are cosine of winding number times theta. It has a prefactor that depends on the monopole mass and the splitting among the different dion states. And it has an exponential prefactor that depends on the monopole mass divided by the splitting. And if you check what this number is in the Atuf-Polyakov case, it's exactly 8 pi squared over g squared. So it's the same as the classical Yang-Mills instanton action. And I think that's not an accident. I think there's some sense in which this thing that you can derive kind of in this effective U1 theory, in the context where you're starting with an non-abelian gauge group and Higgsing it, this is somehow like the instanton sort of evaluated at the scale where the Higgsing cuts off the growth of the instanton size. And this looks a lot like previously derived formulas, for instance, in the theory called extra natural inflation. You imagine an extra dimension and you have an axion that comes from a Wilson line around the extra dimension, and it gets a potential from charged particles with world lines wrapped around the extra dimension. And the formula is basically the same. And the reason is that this, from the point of view of the monopole, there is an extra dimension, and it's the collective coordinate that the monopole can move in. Okay, so yeah.
A comment. There was actually a calculation. I don't know whether it's similar, but at least it has some similar words associated with it by Mithat Unsal and Eric Popitz. They were considering deformation in 3 dimensions, compactifying 1 dimension of Yang-Mills theory. And then there are some fractional instantons which are related by Poisson resummation to dions in 4D. The result is different though. The theta dependence is like theta over n, like you expect in 4D Yang-Mills theory, confining theory. So maybe that was the point. Maybe this is not a confining regime, since you're treating dions as heavy and semi-classical. So, but
right,
just
we're not treating confinement. Yeah, thanks for pointing that out. I should take a look. I've read some of those papers before. I should go back and take a look. I guess in general, I mentioned extra natural inflation, but there's this whole set of calculations that rely on kind of thinking about wrapping an extra dimension, and they all kind of behave similarly. And there are old calculations of Hosotani for extra dimensional theories, and then I know Mithat has gotten a lot of mileage out of this in different applications, compactifying 4D to 3D. So yeah, it's possible that there's a close physical relationship, but there's certainly a close mathematical relationship between the form of those calculations in many different settings, and they give you similar answers. But yeah, thanks for pointing that out.
No problem.
Okay. So what I want to say about this is just that, for the Atuf-Polyakov monopole, we can be very explicit about the formulas and everything, but really the logic here should apply to any monopole with a theta f wedge f term. The theta f wedge f term requires the existence of the dion degree of freedom because that's the only way to make the Whitman effect make sense. And then the semi-classical argument is going to depend on some coefficient on the world line that appears in front of the kinetic term of that compact scalar, kind of the radius of the compact scalar. But roughly speaking, we kind of expect that it's going to give an answer for this instanton action of order 1 over the gauge coupling squared. And for the Polyakov monopole, we got 8 pi squared over g squared. In general, it might be some other constant that goes here. But we kind of think this is going to be very general. And because of this Chern-Weil perspective that I mentioned earlier, we expect that these instantons should not really be independent of other instantons in the theory. So like in the case when we start with SU2 and Higgs, if this instanton was sort of totally unrelated to the Yang-Mills instantons in the UV, it would be as if there were 2 different conserved charges, and that would be like having some extra global symmetry. And we don't really think that happens because we can get this kind of effective theory in the gravitational context where we don't believe that these global symmetries exist. And so I think that what should be true is that these instantons can somehow be continuously deformed into Yang-Mills instantons in the context of the Polyakov monopole. I think that in other contexts, like when we get U1s from D-brane models in string theory, they're not coming from non-abelian things in the UV, they're just a single gauge field living on a single brane. There's a different kind of instanton we can talk about, which is if our U1 gauge field lives on a DP brane, there are instantons that that come from wrapping a Euclidean brane on the same cycle that you wrap that brane on to get your 4D gauge theory. Whereas the monopoles are like some other brane of even higher dimension that kind of ends on the brane where your U1 gauge field lives. And so they're 2 different kinds of D branes, but again, there ought to be some way to sort of deform one into the other, we think. And so it would be good to make that more explicit, which we haven't done yet. But we think that this is all consistent with sort of the Chern-Weil picture, that we don't really have independent instanton effects. But the nice thing about the way we've been talking about it is that you can totally do it from the IR point of view. You don't have to know if it came from a non-abelian gauge theory or from a single D brane or what in the UV. You can just kind of deduce from general principles that something like this should exist. And there's more to say about the story. The potential has to vanish if you have massless charged fermions, because you can do a field redefinition where you rotate the fermion phase in a theta-dependent way. And the way that happens is related to which is some interesting axion or interesting models from the 1980s. So there's more to say about this, and we're working on a follow-up where we explore that in more detail. Okay, I guess I've gone a bit slower than I anticipated, so I don't have a lot of time for the last part. Let's see. Maybe I'll try to just briefly outline some of the statements. So the last thing I wanted to tell you about is we've been thinking about this link between completeness and global symmetries. And in the case of a U1 gauge theory, there's a simple statement you can make, which is that if you have no electrically charged particles, then you have a conserved current star F. But if you have charged particles, you break this conservation law. And in the picture of these symmetry operators, that's related to the fact that we had this operator implementing our one form symmetry, which kind of encircles a Wilson line and produces a phase. But it's supposed to be a topological operator, and you can see that can't be true anymore if we have charged particles, because then we can end the Wilson line on a charged particle, and we can just kind of slide our symmetry operator off the end of the Wilson line, and then we shouldn't get any phase at all when we shrink this operator. And so so this tells you that these operators are not really topological, and the symmetry must be broken unless the phase associated with this was such that the phase that we get here is 1, which happens only for Zn. Okay, so if you have a charge n particle, you break the U1 one-form symmetry to a Zn subgroup. And if you want to completely break the symmetry, you need particles of all possible charges to exist. Okay, so Wilson lines being able to end is in one-to-one correspondence with explicitly breaking the one-form symmetry. And the question is whether there's a general analog of this for arbitrary gauge groups. And there's one other related question we can ask, which is about a different kind of operator, which is that if you have some discrete structure in your gauge group, you could have another kind of object that could exist, which we call a twist vortex or twist string. And this is something where when you take a particle charge under your gauge group and you move it around the vortex in a circle, it picks up a holonomy. It transforms under the gauge group. The simplest example is when you have some discrete symmetry, and this is like an Aharonov-Bohm phase. And Krause and Wilczek talked about this in the context of Z and gauge theory. You can have these Zn strings labeled by some integer k, and when you circle a charge q particle around them, you get a phase of e to the I qk over n. Sorry, I should have a 2 pi here, 2 pi I qk over n. And you can ask about completeness of the spectrum of these. So given a gauge theory, do all of these twist objects actually exist as dynamical objects rather than just sort of probe operators? And if they do exist, is that correlated with the breaking of any global symmetry? And because it's already just about 1 hour into my talk, let me just briefly summarize the punchline. And if people want to ask questions afterwards, maybe we can chat more about it. But then if people want to leave, you could go ahead and leave. So the very brief summary is it's known that you might guess that there's a general theorem that one-form symmetries in gauge theory exist whenever you have an incomplete spectrum, and vice versa. If you have an incomplete spectrum, you have an incomplete spectrum if and only if there's a one-form global symmetry. And that's known to be false. Harlow and Oguri had a counterexample. They showed that in S4 gauge theory, so you have a discrete gauge theory, you can have an incomplete spectrum, but not a one-form symmetry. And so there can't be an if and only if for ordinary symmetries. But Tom Rodelius and Shuhong Xiao in a paper last year proposed kind of a conjecture, which is that you'll have all possible charged particles, states in any representations. You'll have a complete spectrum, if and only if there are no topological Gukov-Witten operators. And a topological Gukov-Witten operator turns out to be something more general than a one-form symmetry. And the reason it's more general is these operators don't form a group. They have a more complicated fusion rule, so you can stack them on top of each other and write down some multiplication rule where you rewrite, a sum of you rewrite a product of these operators as a sum over other operators. But it's not like a gauge theory where you just have a simple multiplication law. It's what we're calling a non-invertible symmetry. People have called these kind of things categorical symmetries or fusion symmetries, or there are different words that have been attached to this in different contexts. And basically, let me just tell you our punchline. We've been able to prove this for arbitrary gauge groups, arbitrary compact gauge groups, whether they have discrete pieces or not. Particles of all possible charges, all representations exist if and only if there are no topological Gukov-Witten operators. And we've also been able to prove that all the twist vortices exist if and only if there are no topological Wilson line operators. Okay, so in U1 gauge theory, Wilson lines are never topological, so this is maybe a less familiar notion, but for instance, in discrete gauge theories, you have topological Wilson lines, and you can prove that they cease being topological whenever these twist vortices like Krause-Wilczek strings exist. And one reason that I'm excited about this claim is that the statement about no topological operators sounds like a natural generalization of the statement of no global symmetries. And I don't know how to argue that quantum gravity doesn't have these operators, but it seems like a reasonable guess that quantum gravity never produces effective field theories containing topological Gukov-Witten or Wilson operators. And if that's true, then quantum gravity theory should not only have particles of all possible representations of the gauge group, they should also have all possible twist vortices. And in 4 dimensions, these twist vortices are like cosmic strings. And as a phenomenologist, that's exciting to me because cosmic strings are things that potentially have implications where you can go, point your telescope at the sky and see something interesting that came from a cosmic string that was produced in the early universe. Okay, so just to give you one example, in the case of O2 gauge theory, there's a discrete part of the gauge group, which is a Z2 where you gauge charge conjugation. And the associated twist vortex is something that back in the 80s and 90s, people studied, and they called it the Alice string. And this is kind of an exotic object where when you move an electron in a circle around an Alice string, it turns into a positron. And so we would say that anytime you have an O2 gauge theory in quantum gravity, we think these Alice strings should be not just hypothetical probe things you can put in, but actual dynamical objects in the theory. Okay, so because I'm going a little bit over time, let me conclude here. We think that quantum gravity doesn't have global symmetries. And global symmetries are familiar concepts, but it turns out that there's kind of this rich universe of global symmetries that's more general than what we usually think about. And Gaiotto and collaborators took one step in this direction by defining these P-form global symmetries back in 2014. But what we're starting to think now is that we should also consider things like non-invertible symmetries, which have also been discussed for a long time, going back at least to the 80s. In terms of fusion categories inside CFTs, but they're really ubiquitous and maybe kind of understudied in higher dimensional gauge theory. And we think that those are also symmetries that probably quantum gravity should not have. And if you take that seriously, it leads to lots of interesting implications. So the fact that we shouldn't have Chern-Weil symmetries in quantum gravity, there are different ways to get rid of those symmetries, but one way is through Chern-Simons terms, and that seems to be a way that string theory makes use of, and that kind of gives us a motivation for why string theory has so many of the ingredients it has: localized world volume degrees of freedom and axions and so on. I've argued to you that these localized degrees of freedom on magnetic monopoles lead to an axion potential. That's not directly related to the statement of no global symmetries, but it's kind of just an interesting fact that could be relevant for thinking about axion physics in the real world. And the absence of even more general kinds of global symmetries should tell us that cosmic strings could exist in the real world in many theories, and that's another exciting thing that we can connect to actual observations. And so I'm excited about this because these very general ideas about topological operators and fusion categories and everything sound kind of abstract and mathematical, but I think they have lots of connections to particle physics and cosmology, and maybe to things that we could actually go look for in the real world and hopefully discover in the future. So thank you.
Let's thank Matt for that wonderful talk. If anyone has any questions for the speaker, you can ask me.
Sorry, I had one question about the last part of your talk.
Okay.
Yeah, so what happens in confining theories? So you said you had this thing about completeness, right? But if the theory is confining, then you don't have charged particles in the theory, right? Asymptotically,
Right.
So,
that's a good question. Yeah, there are different definitions you might imagine giving, but the definition we really rely on is the statement about endability of Wilson lines or Gukov-Whitman operators. And so there are different perspectives on this. So in the paper by Harlow and Oguri, they talked about what they call the long range gauge theory. And so if something confined at short distances, they kind of don't care about it. And that's a reasonable perspective to take. But we think that a stronger statement should be true. And so for us, we're interested in the question of whether a Wilson line can end. And that's a statement that doesn't care about whether the theory confines or not, right? So like in QCD, I could have some heavy quarks and my theory could confine at low energies. But the fact that there are quarks in the theory and the fundamental does mean that I have my Wilson line operators. I can define them in the UV where I know that I have gluons, and they can end on the quarks. And that's a question we're allowed to ask, even though to a long range observer, that might not be relevant for the physics that they can see. And so so by defining, yeah.
Sorry, you're saying finite in finite volume regions, you'd still have charged particles. So you're still sensitive.
Yeah, good. That's one way to say it, right? Yeah, I guess in general, we're imagining that quantum field theory is something we should be able to define on arbitrary manifolds, and so yeah, if you like, you could say, well, let's just go to finite volume on a small space, and then we don't have to worry about confinement, and we can ask these questions. But I think that by defining things in terms of Wilson operators and Gukov-Whitman operators, we have kind of clean definitions that don't really care about the infrared phase of the theory.
Thanks.
More questions?
I have a quick question. I mean, you haven't talked much about I mean, you mentioned at the beginning the evidence for why gravity would dislike this, but I mean, how strong are these statements, and in what realm are we certain? Is it? And I apologize, I don't know much about this topic, but I mean, are we certain that there is no consistent, or not certain, but I mean, how convinced are we that no global symmetries can exist in a theory of gravity?
Yeah, I think that's a fair question. The arguments are often in limited context. So like the Banks-Seiberg argument, I think, is convincing for things like a U1 symmetry, but not at all convincing for, say, a Z2 or Z3 symmetry, because then you only have a couple of possible charges and there's nothing very interesting to say about it. The Harlow-Oguri argument is a nice general argument that seems to apply to a lot of things. It seems to apply to discrete symmetries as well as continuous ones. It seems to apply to, I guess, anything from a zero form symmetry up to a D minus, forgetting if it stops at D minus 2, I think D minus 2 form symmetry. But it relies on holography and having an asymptotically ADS space. And so you could say, you know, that's not the universe we live in. So how do we know that the same thing applies? I think some of these other more recent papers have tried to sort of argue that these ingredients should kind of apply beyond that context, but I don't think we have completely airtight arguments. Another thing you might say is that, you know, I told you that no topological operators should exist in quantum gravity, and I don't have a good argument for that. One thing people could say as an argument for that is that, in fact, no local operators at all exist in a theory of quantum gravity, because a local operator doesn't play nicely with the diffeomorphism invariance of the theory. But that's somehow kind of unconvincing, because at least within EFT, we know that you can get really, really, really close to having local operators. So maybe we shouldn't be satisfied with that kind of abstract statement. There's kind of an even stronger statement than no global symmetries that Jake McNamara and Cameron Baffa formulated, which is the no cobordism conjecture, which implies a lot of these other things, including the absence of -1 form symmetries. But it's a conjecture. It's not. There's not a super sharp argument in favor of it. So yeah, I think our attitude with a lot of these things is we have strong evidence against certain kinds of global symmetries in certain kinds of contexts. If they were absent completely, let's just see what would happen. You know, do we run into any problems, or do we learn interesting things? And my feeling is that it's probably true in complete generality, but I certainly can't prove it to you. And so when I say that I believe this kind of thing implies that like certain theories in the real world would predict the existence of cosmic strings, I am making some assumptions that I can't completely justify. So I think it would be great if we have more work on this question, aimed at not only the standard global symmetries in different kinds of backgrounds, but at things like -1 form symmetries or non-invertible symmetries, some of these more exotic things. And if people could provide us with strong arguments for why those shouldn't exist in quantum gravity, I think lots of interesting phenomenological applications could follow from that. And I think maybe that's something that's hasn't been appreciated by say part of the string theory community, where people are interested in these as kind of abstract formal questions. I got into this because I'm a particle physicist, and I would be super excited if we could find axions or find cosmic strings. And I think to me, it's really exciting that there's this common ground between super formal things and things that we can actually go look for in the real world.
Thank you.
Mm-hmm.
Okay, if there are no more questions, let's thank the speaker once again, and see you guys next time. Thanks.
Thank you.